Here is the CAD model of the motorcycle helmet we will be working on. It's a full-face helmet designed to be used on the road or for races. From front to back, the helmet is 313 millimeters long, and from the left and right sides is 270 millimeters wide. This is similar to common helmet sizes and provides ample room for our PCM to be implemented.
As we mentioned in this previous slide, the helmet we designed is approximately 313 millimeters in length and 270 millimeters in width. Based on this structure, we are planning to place PCM all around the head, specifically front, top, and back section. The PCM will be located under the outer shells of the helmet. Since the helmet has a curved internal shape, the estimated size of the PCM insert will be around 320 to 330 millimeters in length and 270 to 290 millimeters in width, with a thickness of about 1 to 3 millimeters. As shown in this cross-sectional views of prototype 1 and 2, we are exploring different configurations to optimize coverage, comfort, and cooling efficiency while maintaining the helmet's structural integrity.
We decided that the most optimal placement for the PCM would be at the top of the helmet. This was for two main reasons. Firstly, the top of the helmet is in contact with direct sunlight, so it gets heated up the fastest. And this could cause discomfort for the rider unless the PCM was there. And secondly, thanks to the air vents at the top of the helmet, when the PCM is placed at the top of the helmet, the PCM will be able to dissipate more heat, thus making it a more comfortable ride for the rider.
Hello, my name is Ahmed, and today I'll be presenting the further studies, the mesh and simulations that we want to do for part of the helmet. So for the target area, I have chosen the PCM pouch section, as it can be seen on the figure on the right side, where the PCM is placed on the helmet, and the position between the helmet, which is the outer space, and the helmet foam. The objective of this is to assess if the location is ideal for the PCM placement, and it was previously mentioned, and evaluate the effectiveness in improving the rider's comfort without affecting the helmet safety. So we're going to do some further studies and simulation to focus on the thermal performance of the PCM, the cooling effect during the riding, and the structural impact of the PCM addition. We'll also use a meshing approach to refine the mesh on the PCM pouch area to accurately find out the heat transfer and temperature distribution by analyzing it, do a detailed mesh at the PCM helmet interface, and find out the balanced mesh density to reduce the simulation time.
The number of elements in a mesh determine whether the mesh is coarse or fine. There are a couple of ways in which you can change the number of elements in a mesh. For example, on the left we can see that there are different types of meshes. When using different types of meshes, the number of elements in the mesh changes. In the example we have here, when using a triangular mesh of the same size as the quadrilateral mesh, the triangular mesh has 1200 elements, while the quadrilateral mesh only has 549. Meaning that the triangular mesh is twice as fine as the quadrilateral, even at the same size. And the other way in which you can change the number of elements in a mesh is by changing the size of the mesh. On the right hand side, we can see three different sizes of meshes named N, 2N, and 4N. As we can see, N has 520 elements, 2N has 1012, and 4N has 2072. This shows that when the size of the mesh gets doubled, the number of elements also gets doubled.
I made 3 meshes with different element numbers. I chose to use quadrilateral mesh due to them being superior at visual representation and animation. With the coarse mesh, the top and bottom sides have 12 divisions, and the left and right sides have 30, which leads to 390 elements, or 780 if I had chosen to use triangular mesh. The fine mesh has 768 elements, with 24 divisions on the top and bottom, and 30 on the left and right sides. 2n has a value of 1.969 times n. The very fine mesh has 1,560 elements. There are 26 divisions on the top and bottom sides, and 60 on the left and right sides. There are exactly 4n elements.
For my individual task, I generated 3 different mesh densities based on the n, 2n, and 4n guideline. Mesh 1 has 931 nodes and 858 elements. Mesh 2 has 1,851 nodes and 1,726 elements. Mesh 3 has 3,599 nodes and 3,458 elements. The number of nodes and elements approximately doubles and quadruples from the first mesh, which follows the expected sizing rule. However, even though the total count increases, most of refinement is concentrated around the curved edge region. The center area of the mesh stays almost the same in all 3 cases. If the center region needs more detail in simulation, it will require manual sizing or local refinements. But if the center doesn't have significant flow or heat changes, this distribution might still be acceptable.
So for this slide, I've talked about my meshes. So I've broken them into type of meshes and element mesh sizing. So for the type of meshes, I've chosen the triangular and quadrilateral mesh to differentiate which one would be better for our helmet. So quadrilateral mesh would be much better to use in this case because due to its size and its flexibility. I've also broken that into the nodes and elements as well. So when doing the calculation for the triangular mesh, we have 28 triangles from left to right, and then 35 triangles from top to bottom, which give us 840 elements. For quadrilateral mesh, for the type of meshes, we have 14 rectangles from left to the right, and 25 rectangles from top to bottom, which give us 350 elements. And for element mesh sizing, I wanted to figure out how the ends would work if I were to increase them by 2 times and 4 times. So my n value, I had 555 elements. When I times it by twice, so 2n, I got 1080 elements. And I did the same for 4n, which I times by 4 and got the elements of 2156.
So I did 4 different meshes. The first one is a triangular mesh titled N with 1281 nodes and 2400 elements with 60 by 20 divisions. The second mesh that I had is a quadrilateral mesh, so the same amount of nodes but half the elements with 1200 elements and the same amount of divisions as the triangular mesh N. I had a third mesh which was the quadrilateral mesh 2n. It had 4,961 nodes and 4,800 elements, so 4 times the amount of elements from the quadrilateral mesh n, with double the amount of divisions, so 120 by 40. And the fourth mesh that I had was a quadrilateral mesh titled 4n with 19,521 nodes and 19,200 elements, with double the amount of divisions from the second quadrilateral mesh 2n by, so the dimensions for that would be 240 by 80.
So in this slide, I had a look at the health safety issues and possible solutions we can come up with. So I based on the type of PCMs they're using and based on the helmet, the actual structure of the helmet. The first point was the leakage risk, so the paraffin wax. The issue was that paraffin wax can leak if the PCM pouch is damaged in the inside, and the solution was to use a double sealed PCM pouch and add a protective outer layer around the PCM in order to keep it sealed and not leaking. Flammability, so burning up, was also one of the issues at high temperatures, and for this we'll use fire resistant outer materials, limit the PCM quantity to reduce the risk, which we are only using one, and then thermal insulation to prevent overheating. Third one we came up with was toxic fumes in fire. So burning paraffin wax can release toxic fumes, which was very toxic for if you were to inhale it. And for this, we were going to design the PCM pouch with a fireproof containment. So if it does burn up, or when we burn it to make it to put in the shape, it doesn't give us any harmful fumes, and also to include a warning label around the material content, so inside the helmet or on the packaging we'll add one. Also the weight, added weight and balance was a big issue as well, because if the extra weight may affect the helmet balance and comfort when somebody is wearing it for a short term or a long time. And for this, we're going to distribute the PCM evenly on top of the helmet. So when we do, it will be from one side to other side, evenly spaced out. And then we're planning to keep the PCM weight around 5% of the total helmet weight, so it doesn't just sits on and just drop it down. And for the fifth was the structural weakness. So integrating the PCM pouch may weaken the helmet outer shell in case of impact, in case there was a injury or there was an accident. If the PCM pouch was too weak, it might actually damage the person who is wearing it. And the solution was to place the PCM only in the non-critical areas and conduct impact testing after the PCM integration. So we'll do further simulations, and we'll also do testing as well when everything is done. And so the next slide is talking about our references that we use, and that's it from us. Thank you for listening. Have a good day.